1 light year. Right now, at this very second, something extraordinary is happening all around you. Light, the fastest thing in the entire universe, is racing past you at an almost incomprehensible speed. It is moving at exactly 299,792,458 meters every single second. That is not an approximation. That is not a rough estimate. That is the exact, precise, unwavering speed of light in a vacuum. And in the time it took you to read that sentence, light has already traveled far enough to circle the entire Earth more than once. Think about that for a moment. The entire Earth, all 40,075 kilometers of its equatorial circumference, and light just wraps around it like it is nothing. In fact, light can circle the Earth approximately 7.5 times in just 1 second, 7.5 times. In 1 heartbeat, light has gone around the world 7 times and then some. That is the speed we are dealing with today. That is the starting point of our journey. And here is where things get truly mind-bending. If light is that fast, if it can circle our planet nearly 8 times in the blink of an eye, then how far does it travel in an entire year? Not a second, not a minute, not an hour, not a day, an entire year. 365.25 days of non-stop, relentless, full-speed travel. The answer to that question is what we call a light year, and I promise you by the end of this video, you will never look at the night sky the same way again. But before we dive into the depths of this cosmic measurement, let me ask you something that might keep you up tonight. When you step outside and look up at the stars, do you realize that you are not looking at the present? You are looking at the past. Every single star you see is showing you light that left it years, decades, centuries, or even millennia ago. The star Betelgeuse, that bright reddish star in the constellation Orion, is about 700 light-years away. That means the light hitting your eyes tonight actually left Betelgeuse around the year 1326. That was the Middle Ages. Knights were riding horses into battle. The Black Death had not yet ravaged Europe, and that light was already on its way to your eyes. Now, here's the terrifying part. Betelgeuse might have already exploded. It might have gone supernova hundreds of years ago, but we would not know yet because the light carrying that information has not reached us. We are literally watching a star that might already be dead, and we will not find out for centuries. That is the power and the strangeness of what a light year really means. Now, let me hit you with another question that I want you to really sit with. Our fastest spacecraft ever built, the Parker Solar Probe, has reached speeds of approximately 692,000 kilometers per hour. That is absurdly fast. That is fast enough to travel from New York to Los Angeles in about 20 seconds. And yet, if you pointed the Parker Solar Probe at the nearest star system, Proxima Centauri, which is just 4.24 light-years away, it would take over 6,600 years to get there. Not 6,600 days, not 6,600 months, 6,600 years. For context, 6,600 years ago, human beings had not yet invented writing. The Egyptian pyramids did not exist, the Bronze Age had not started. That is how long our fastest spacecraft would need just to reach the nearest star. And that is only 4.24 light-years. The Milky Way galaxy, our home galaxy, is about 100,000 light-years across. The nearest major galaxy, Andromeda, is 2.537 million light-years away. The observable universe stretches approximately 93 billion light-years from one end to the other. The numbers become so enormous that our brains literally cannot process them. We are not designed to comprehend these scales. Our ancestors evolved to understand distances like, how far is that tree? Or, how far is the next watering hole? We did not evolve to wrap our minds around trillions of kilometers. But today, we are going to try. And we are going to do it together, step by step, piece by piece, until the true scale of the cosmos begins to crystallize in your mind. So, what exactly are we going to cover in this video? Let me tell you, because this is going to be a deep, comprehensive, mind-expanding journey. We are going to start by understanding what a light year actually is, not just as a number, but as a concept, as a reality, as a distance that exists between us and the stars. We are going to explore the speed of light itself, how it was discovered, how it was measured, and why it is the ultimate speed limit of the universe. Then, we are going to do something that I find absolutely fascinating. We are going to calculate how long it would take to travel 1 light year at various speeds, starting from walking pace to driving speed, to airplane speed, to the speed of sound, all the way up to the speeds of our actual spacecraft. We will examine every real spacecraft humanity has ever launched and calculate their travel times. We are going to explore theoretical and future technologies that might one day close this impossible gap. We will dive deep into Einstein's theory of relativity and how it changes everything about how we perceive time and distance at high speeds. We will look at exotic ideas like warp drives and wormholes. We will examine what actually exists in the space between stars, because it is not just empty void. We will tackle the Fermi paradox and how light-year distances might explain why we have not found alien civilizations. We will look at the philosophical and existential implications of living in a universe where distances are so unimaginably vast. And by the end, I promise you, you will have a profound, almost meditative understanding of what it truly means to travel 1 light year. This is not just a science video. This is a journey into the fundamental nature of the universe we inhabit. So, please, if you are excited about this journey, and I sincerely hope you are, take a moment to hit that like button. Subscribe to this channel if you have not already, because we go deep into topics like this regularly, and ring that notification bell so you never miss an exploration like this one. Now, let us begin. Let us start with the very basics, because I think it is crucial that we build our understanding from the ground up. A light year. The term itself is deceptive. When most people hear light year, they instinctively think it is a unit of time. It has the word year right there in the name. So, how could it not be about time? But here's the truth. A light year is not a unit of time. It is a unit of distance. Specifically, it is the distance that light travels in 1 Julian year, which is defined as exactly 365.25 days. This distinction is absolutely fundamental to everything we are going to discuss today. When an astronomer tells you that a star is 10 light years away, they are not saying it takes 10 years to get there. They are saying that the distance between us and that star is equal to the distance light covers when it travels for 10 years at its full speed in a vacuum. And that distance is enormous. Let me break down the exact calculation so you can truly appreciate the scale. Light travels at 299,792,458 meters per second. Let us round this very slightly and work through the math. In 1 minute, that is 60 seconds, light travels approximately 179,877,547,480 meters, or roughly 17.99 million kilometers. In 1 hour, which is 3,600 seconds, light covers about 1,79,252,848,800 meters, or approximately 1.079 billion kilometers. In 1 day, 24 hours, light travels about 25,900 2,068,371,200 meters, or roughly 25.9 billion kilometers. Think about that. In a single day, light covers almost 26 billion kilometers. That is a distance so vast that it dwarfs the diameter of our entire solar system out to Neptune. And now, multiply that daily distance by 365.25 days, the length of one Julian year. The result is approximately 9,730,732,472,580,800 meters. Written out more intuitively, that is about 9.461 trillion kilometers. Let me write that with all the zeros so the full weight of it hits you. 9,461 billion kilometers. That is one light year, just one. And the nearest star is more than 4 of those away. The galaxy is 100,000 of those across. The observable universe is 93 billion of those in diameter. We are dealing with numbers that the human mind was simply never designed to grasp. The term light year has an interesting history. It was not always the standard unit of astronomical distance. In the early days of astronomy, people measured distances within our solar system using what we now call the astronomical unit, which is the average distance between the Earth and the Sun, approximately 150 million kilometers. This worked well enough for planets, moons, and asteroids. But as astronomers began to understand that the stars were not just dots on a celestial sphere, but were in fact distant suns, unimaginably far away, they needed a new unit. The concept of using light travel time as a distance measurement gained traction in the 19th century. Friedrich Bessel, the German mathematician and astronomer who made the first successful measurement of a star's distance using stellar parallax in 1838, was one of the key figures in establishing the need for such enormous distance units. He measured the distance to the star 61 Cygni and found it to be about 10.3 light-years away. This was the first time humanity had a real, measured number for the distance to another star, and the numbers were staggering. Suddenly, the universe was not just big. It was incomprehensibly, overwhelmingly, almost oppressively vast. To give you a sense of this scale, let me walk you through some distances within and beyond our solar system, all expressed in light travel time. The Moon, our closest celestial neighbor, is about 384,400 kilometers from Earth. Light covers that distance in approximately 1.28 seconds. So when you look at the Moon, you are seeing it as it was about 1.3 seconds ago, practically the present, as far as cosmic distances are concerned. Now, the Sun, our Sun is about 149.6 million kilometers away, which means sunlight takes approximately 8 minutes and 20 seconds to reach Earth. This means that if the Sun were to suddenly vanish right now, not that it could, but hypothetically, we would not know about it for over 8 minutes. We would continue to see its light, feel its warmth, orbit its gravity for 8 minutes and 20 seconds before the darkness and gravitational freedom reached us. Moving outward, Mars, at its closest approach to Earth, is about 55 million kilometers away, which is roughly 3 light minutes. Jupiter, the giant of our solar system, is about 35 to 52 light minutes from Earth depending on orbital positions. Saturn is roughly 67 to 85 light minutes away. Neptune, the outermost planet, is about 4 to 4.15 light hours from Earth. And the hypothetical edge of our solar system, defined by the Oort cloud, that vast shell of icy objects that surrounds our solar system, extends out to roughly 1 to 2 light-years from the Sun. So our solar system, as enormous as it is, spanning light hours from the Sun to Neptune, is actually contained within a boundary that is 1 to 2 light-years in radius, and the nearest star is 4.24 light-years away. there is an enormous gulf of nothing, of empty interstellar space between the edge of our solar system and the next star. And traversing that gulf is the challenge that defines the limits of human exploration. Let me give you some analogies that might help your brain process these scales, because raw numbers, no matter how precisely calculated, often fail to convey the emotional and intuitive understanding of how truly vast these distances are. Imagine you are holding a basketball. That basketball represents the Earth. On this scale, the moon would be a tennis ball about 7.4 meters away. The sun would be a massive ball about 26 meters in diameter, think of a large house, and it would be positioned about 2.8 kilometers away from your basketball Earth. Already, that is a city-spanning model just for Earth and the sun. Now, where would the nearest star, Proxima Centauri, be on this scale? Proxima Centauri, scaled down proportionally, would be about 780,000 kilometers away from your basketball Earth. That is about twice the actual distance from the Earth to the real moon. Think about that. In a model where the Earth is a basketball you can hold in your hand, the nearest star is as far away as the moon is in real life. That is how empty and vast space truly is. Here is another way to think about it. Imagine the entire solar system, from the sun out to the orbit of Neptune, shrunk down to the size of a small coin, say a US quarter, which is about 24 millimeters in diameter. On that scale, 1 light-year would be approximately 39 meters, and the nearest star, Proxima Centauri at 4.24 light-years, would be about 166 meters away. So, if our entire solar system were a coin in your pocket, the nearest star would be about a block and a half down the street. And the Milky Way galaxy on this scale? It would stretch across the entire United States, and the nearest major galaxy, Andromeda, would be somewhere on the other side of the planet. These analogies help, but even they struggle to convey the true emptiness, the true isolation, the true scale of cosmic distances. We are so incredibly small, and the universe is so incomprehensibly large that it borders on the absurd. Now, let us talk about light itself, because to truly understand the light year, we need to understand the entity that defines it. Light, electromagnetic radiation, the fastest thing in the universe, the cosmic speed limit, the very foundation upon which Einstein built his revolutionary theories. What exactly is light, and why does it travel at the speed it does? Light is electromagnetic radiation. It is a self-propagating wave of electric and magnetic fields that oscillates perpendicular to its direction of travel. It does not need a medium to travel through. Unlike sound, which needs air or water or some physical substance to propagate, light can travel through the complete vacuum of space. This was one of the great revelations of 19th century physics. For centuries, scientists had debated whether light needed some kind of invisible substance, called the luminiferous ether, to propagate through. The famous Michelson-Morley experiment of 1887 effectively demolished the ether hypothesis by showing that light travels at the same speed regardless of the direction of Earth's movement through space. There was no ether. Light simply traveled through empty space at a constant speed, and that speed was always the same no matter who measured it or how they were moving. This seemingly simple observation would later become the cornerstone of Einstein's special theory of relativity, which we will discuss in great depth later in this video. The speed of light in a vacuum is exactly 299,792,458 meters per second. And I mean exactly. This is not a measurement with error bars. Since 1983, the meter itself has been defined in terms of the speed of light. 1 meter is defined as the distance light travels in exactly 1/299,792,458 of a second. so the speed of light is exact by definition. It is one of the fundamental constants of the universe, often denoted by the letter c, which comes from the Latin word celeritas, meaning swiftness or speed. But light does not always travel at this maximum speed. In different mediums, light slows down. When light enters water, it slows to about 225,000 kilometers per second, roughly 75% of its vacuum speed. In glass, it slows to about 200,000 kilometers per second. And in diamond, one of the densest transparent materials we know, light slows to about 124,000 kilometers per second, less than half its vacuum speed. This slowing of light in different mediums is what causes refraction, the bending of light that makes a straw appear bent in a glass of water, that creates rainbows, and that allows lenses in telescopes and microscopes to work. But for the purpose of measuring cosmic distances, we always use the speed of light in a vacuum because the space between stars is, for all practical purposes, a near-perfect vacuum. The history of measuring the speed of light is itself a fascinating journey of human ingenuity. For most of human history, people assumed light traveled instantaneously. When you light a candle, the room is illuminated immediately. When lightning strikes, you see the flash before you hear the thunder, which seemed to suggest that light was infinitely fast. Galileo, in the early 1600s, attempted to measure the speed of light by having two people stand on distant hilltops with covered lanterns. The idea was that one person would uncover their lantern, and when the other person saw the light, they would uncover theirs. By measuring the time delay, Galileo hoped to calculate the speed. But the experiment failed because light was far too fast for human reaction times to detect any delay. Galileo could only conclude that if light was not instantaneous, it was extraordinarily fast. The first successful estimation of the speed of light came from an unlikely source, the moons of Jupiter. In 1676, the Danish astronomer Ole Rømer was carefully timing the eclipses of Io, one of Jupiter's moons, as it passed behind the giant planet. He noticed something peculiar. The timing of these eclipses seemed to vary depending on where Earth was in its orbit relative to Jupiter. When Earth was closer to Jupiter, the eclipses seemed to happen earlier than predicted. When Earth was farther from Jupiter, they happened later. Rømer realized that this discrepancy was caused by the time it took light to cross the varying distance between Earth and Jupiter. When Earth was farther away, the light had to travel a greater distance, so news of the eclipse arrived later. From these observations, Rømer calculated that light took about 22 minutes to cross the diameter of Earth's orbit around the Sun. His estimate was not perfectly accurate. The actual time is about 16.5 minutes, but it was revolutionary. For the first time in human history, someone had demonstrated that light had a finite speed, and they had produced a rough estimate of what that speed was. Over the next 2 centuries, the measurement of light speed was refined with increasing precision. In 1849, the French physicist Hippolyte Fizeau conducted a brilliant experiment using a rapidly rotating toothed wheel. He shone a beam of light through a gap in the wheel toward a mirror about 8 kilometers away. The light traveled to the mirror, bounced back, and returned to the wheel. If the wheel was spinning at just the right speed, the returning light would be blocked by the next tooth, but at a slightly different speed, it would pass through the next gap. By carefully measuring the rotation speed needed to block and unblock the returning light, Fizeau calculated the speed of light to be approximately 315,000 kilometers per second. This was remarkably close to the true value for an experiment conducted with 19th century technology. The following year, Fizeau's colleague Léon Foucault improved on the method using a rotating mirror instead of a toothed wheel, obtaining an even more accurate result. and in the late 1800s, the American physicist Albert Michelson devoted much of his career to precision measurements of light speed, eventually achieving values accurate to within a fraction of a percent of the true value. Michelson's work earned him the Nobel Prize in Physics in 1907, and his measurements stood as the gold standard for decades. Today, we know the speed of light with absolute precision because, as I mentioned, we have defined our units around it. But the fundamental question remains: why is the speed of light what it is, and why is it the universal speed limit? This is where we enter the domain of Einstein. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would reshape our understanding of space, time, and the very fabric of reality. His name was Albert Einstein, and his paper was titled On the Electrodynamics of Moving Bodies. In it, Einstein proposed what we now call the special theory of relativity, based on two deceptively simple postulates. First, the laws of physics are the same for all observers in uniform motion, meaning if you are moving at a constant speed in a straight line, you cannot perform any experiment to determine whether you are moving or stationary. Second, the speed of light in a vacuum is the same for all observers, regardless of their relative motion. This second postulate seems almost absurdly counterintuitive. If you are driving a car at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing on the roadside would see the ball moving at 150 kilometers per hour. That is just common sense. But Einstein said that light does not work this way. If you are in a spaceship traveling at 200,000 kilometers per second and you shine a flashlight forward, someone standing still would not see that light moving at 200,000 plus 299,792 kilometers per second. They would see it moving at exactly 299,792 kilometers per second. The same speed, always, no matter what. This seems impossible, and yet every experiment ever conducted has confirmed it. Light speed is constant, period. The consequences of this seemingly simple idea are profound and reality warping. To make the speed of light constant for all observers, something else has to give. And what gives is our intuitive understanding of time and space. Time slows down for objects moving at high speeds relative to a stationary observer. Distances contract in the direction of motion, and mass effectively increases as speed increases. These are not theoretical abstractions. They are measurable, observable effects that have been confirmed by countless experiments. We will explore all of these consequences in tremendous detail later in this video, because they have enormous implications for what it would mean to actually travel a light year. But for now, the key takeaway is this: the speed of light, 299,792,458 meters per second, is not just a number. It is a fundamental property of the universe. It is the speed at which causality itself propagates. It is the maximum speed at which information, energy, or matter can travel through space. And it is the measuring stick by which we define the light year, the basic unit of cosmic distance. Now I want you to really sit with some facts about the speed of light that help contextualize just how fast it is, because we are about to contrast it with human speeds, and the contrast is going to be staggering. In 1 second, light travels 299,792 kilometers. In that same second, the fastest human ever, Usain Bolt at his peak, covers about 12.4 meters. Light is approximately 24 million times faster than the fastest human runner. In 1 second, light could travel from the Earth to the Moon and back, and still have distance left over. Light covers the Earth-to-Moon distance in about 1.28 seconds, so in 1 second it gets about 78% of the way there. To put it differently, if someone on the moon turned on a flashlight aimed at Earth, you would see it roughly 1.3 seconds later. That is practically instantaneous on a human timescale, but it represents a distance of 384,400 kilometers. In 8 minutes and 20 seconds, light crosses the 150 million kilometers between the Sun and Earth. This is why we say the Sun is about 8.3 light minutes away. If the Sun were to suddenly stop shining, we would enjoy 8 more minutes of daylight, blissfully unaware that our star had gone dark. Light from the Sun takes about 5.5 hours to reach Pluto at its average distance, and light leaving the Sun right now will not reach the Oort cloud, the outermost boundary of our solar system, for about 1 to 2 years. Even light, the fastest thing in the universe, takes years to leave our solar system. And once it does, it still has years more of travel before it reaches the nearest star. That is the scale we are dealing with. Consider this thought experiment. Imagine you are standing on the Sun, and you have a perfectly powerful laser pointer, and you aim it at the Earth. You click it on. For 8 minutes and 20 seconds, nothing happens on Earth. No one sees your laser. No one even knows it is coming. It is racing across 150 million kilometers of empty space. Then, after 8 minutes and 20 seconds, someone on Earth sees a dot of light appear. Now, imagine you swing your laser pointer toward Proxima Centauri, the nearest star. You click it on. For 4.24 years, that beam of light travels through the interstellar void. If someone were on a planet orbiting Proxima Centauri, they would not see your laser for over 4 years. And if they immediately sent a signal back to you, you would not receive their reply for another 4.24 years. A simple, round-trip conversation between our Sun and the nearest star takes over 8.5 years. A conversation. Just saying hello and hearing hello back. 8.5 years. This is the reality of cosmic distances. This is why 1 light year matters. And this is why understanding it deeply changes how you think about everything, from space exploration to the possibility of communicating with alien civilizations. Now, let us embark on what I think is the most viscerally striking part of this entire exploration. Let us calculate, with real numbers and real math, how long it would take to travel 1 single light year at various speeds that we humans are familiar with. We are going to start slow, very slow, and work our way up. And I guarantee you the results will blow your mind. Let us begin with the most basic form of human locomotion, walking. The average human walking speed is approximately 5 kilometers per hour. It is the pace at which you stroll through a park, walk to the grocery store, or meander through a museum. Now, 1 light year is approximately 9.461 trillion kilometers. So, at 5 kilometers per hour, walking non-stop, never sleeping, never eating, never resting, never doing anything but walking at a brisk pace in a straight line through space, how long would it take to cover 1 light year? The calculation is straightforward. 9,461 billion kilometers divided by 5 kilometers per hour equals 1,892,200,000,000 hours. Converting that to years, we divide by 8,766 hours per year, and we get approximately 215,800,000 years. Let that number wash over you. 215,800,000 years. To walk 1 light year. Let me put that in perspective. 215 million years ago, it was the late Triassic period. The dinosaurs were just beginning to rise. The first true dinosaurs like Eoraptor and Herrerasaurus were only just evolving. The supercontinent Pangaea was beginning to break apart. Mammals did not exist yet, at least not in any form recognizable to us. The Atlantic Ocean did not exist. The world was a completely different planet. If you had started walking from Earth toward Proxima Centauri 215 million years ago, at that steady 5 km/h pace, you would just now be arriving at the 1 light-year mark. Not at Proxima Centauri, mind you, because that is 4.24 light-years away. You would still have more than 3/4 of the journey left. At walking speed, reaching Proxima Centauri would take over 900 million years. 900 million years. That is about a fifth of the entire age of the Earth. At walking speed, interstellar travel is so far beyond absurd that it borders on meaningless. But let us speed up. What about running? Let us use the fastest speed a human has ever been recorded moving on foot. Usain Bolt's peak speed of approximately 44.72 km/h, achieved during his record-breaking 100-meter sprint in 2009. If we could somehow maintain Bolt's top speed indefinitely, running non-stop through space at 44.72 km/h, how long to cover 1 light-year? 9,461,000,000,000 divided by 44.72 gives us approximately 211,580,000,000 hours, which converts to roughly 24,130,000 years. About 24 million years. That is better than walking, sure, but 24 million years ago, we are in the late Oligocene to early Miocene epoch. Early apes were just beginning to evolve. The Great Rift Valley in Africa, which would eventually shape human evolution, was just beginning to form. Grasslands were spreading across the continents. Whales were evolving their modern forms. The world was alien and unrecognizable. Running at the fastest speed any human has ever achieved, non-stop for 24 million years, to cover 1 light-year. And the nearest star is more than 4 times farther. What about driving? Let us say you hop in a car and set the cruise control to 120 km/h, a comfortable highway speed. You are driving through space on an invisible road, never stopping for gas, food, or rest. 1 light-year at 120 km/h, 9,461,000,000,000 divided by 120 equals roughly 78,842,000,000 hours, which is about 9 million years. 9 million years. 9 million years ago, in the late Miocene, our distant ancestors were still decidedly ape-like. The lineage that would eventually lead to humans and chimpanzees had not yet split. The Mediterranean Sea had dried up in the Messinian salinity crisis. Saber-toothed cats roamed the earth. If one of our ape-like ancestors had somehow gotten into a car and started driving at highway speed toward the nearest star, 9 million years later, their descendants would still be in the car, and they would have just barely covered 1 light-year. Let me make this even more tangible. At 120 km/h, you cover about 2,880 kilometers per day, which is roughly the distance from New York to Los Angeles. So every day, you are driving a transcontinental distance. And you have to do that every single day for 9 million years to cover 1 light-year. The futility is almost beautiful in its extremity. How about we think about this in terms of fuel cost, just for fun? A typical car gets about 10 kilometers per liter of gasoline. To drive 9.461 trillion kilometers, you would need approximately 946 billion liters of gasoline. At current fuel prices of roughly $1.5 per liter, that is about $1.42 trillion. That is roughly 7% of the GDP of the entire United States, and that is just the fuel cost for one car to drive 1 light-year. No maintenance costs, no tire replacements, no oil changes, just fuel. For a single, impossible 9 million year road trip. Space is so vast that even our economic metaphors collapse under the weight of the numbers. Let us try something faster. A high-speed train. The current world speed record for a conventional train is 574.8 kilometers per hour, set by a French TGV train in 2007. At that blistering speed, 1 light-year would take 9,461,000,000,000 divided by 574.8, which equals roughly 16,460,000,000 hours, or about 1,878,000 years. Nearly 1.9 million years. That takes us back to the early Pleistocene, when Homo habilis, one of the earliest members of our genus Homo, was using crude stone tools in East Africa. The first ice ages were beginning. Mammoths were starting to roam the northern continents. If a Homo habilis had somehow boarded a bullet train and sent it hurtling toward the nearest star at record speed, their descendants, nearly 2 million years of evolution later, modern humans who have built civilizations, written literature, split the atom, and landed on the moon, would still be on that train. Still not 1 light-year from where they started. What about commercial air travel? A typical jet airliner cruises at about 900 kilometers per hour. At that speed, 9,461,000,000,000 divided by 900 equals approximately 10,512,000,000 hours, or about 1,200,000 years. 1.2 million years. That is deep in the Pleistocene. Homo erectus was the dominant hominin species. They were using fire and making sophisticated hand axes. Glaciers were advancing and retreating across the northern hemisphere. Humanity, as we know it, was still hundreds of thousands of years from existing. A non-stop flight at commercial jet speed, lasting 1.2 million years, to cover 1 single light year. To reach the nearest star, you would need to fly for about 5 million years. 5 million years of continuous flight. The airline miles would be astronomical. Pun very much intended. Let me now go even faster. The speed of sound in air at sea level is approximately 1,235 kilometers per hour, also known as Mach 1. Military fighter jets routinely exceed this speed. At Mach 1, 9,461,000,000,000 divided by 1,235 equals approximately 7,659,000,000 hours, or about 873,900 years, almost 874,000 years. Homo heidelbergensis was walking the Earth. They were ancestors to both modern humans and Neanderthals. Complex tools were being developed. The world was still locked in the ice ages. Even at the speed of sound, which was considered an insurmountable barrier for human flight until Chuck Yeager broke it in 1947, 1 light year is simply beyond reach in any time frame that makes sense for human experience. What about the fastest jet aircraft ever built? The SR-71 Blackbird, that legendary Cold War spy plane, held the speed record for air-breathing jet aircraft at approximately 3,530 kilometers per hour, or roughly Mach 3.3. This incredible machine could fly from New York to London in less than 2 hours. At its top speed, 9,461,000,000,000 divided by 3,530 equals approximately 2,679,600,000 hours, or about 305,700 years. About 306,000 years. That brings us to a time when Homo sapiens, our own species, was just emerging in Africa. The earliest anatomically modern humans were taking their first breaths. At the speed of the fastest jet ever flown, it would take the entire existence of our species so far, roughly 300,000 years, to cover 1 light year. Our entire species. Every single human being who has ever lived, from the first Homo sapiens in Africa to you reading this right now, could fit within the time it would take the Blackbird to fly 1 light year. and we still would not quite be there. Let us push to the fastest speed achievable by a projectile. The fastest rifle bullets travel at about 1,800 meters per second, which is 6,480 kilometers per hour. At that speed, 9,461,000,000,000 divided by 6,480 equals approximately 1,460,000,000 hours, or about 166,600 years, about 167,000 years. That puts us in the Middle Pleistocene. Humans were migrating out of Africa. Neanderthals were thriving in Europe. The world was cold, harsh, and sparsely populated. Even a bullet, one of the fastest objects in our everyday experience, would need 167,000 years to traverse 1 light year. And now, here is what makes all of this so staggering. Everything we have calculated so far, every one of these mind-bending numbers, represents a speed that is so slow compared to the speed of light that it barely registers. Walking at 5 kilometers per hour is 0.000000015% the speed of light. A car at 120 kilometers per hour is 0.000000037% the speed of light. The fastest bullet at 6,480 kilometers per hour is 0.0000060% the speed of light. We have not even come close to 1/1,000,000% of light speed. The gap between our everyday speeds and the speed of light is not just large. It is incomprehensibly, jaw-droppingly, cosmically enormous. Light is so fast that our entire range of human experience, from walking to bullets, occupies an invisibly tiny sliver at the very bottom of the cosmic speed scale. This is why space is so hard. This is why the stars are so far. This is why 1 light year is such a monumentally, overwhelmingly vast distance. Now, let us leave the realm of everyday speeds and enter the world of spacecraft. These are the fastest machines humanity has ever built. Objects that represent the absolute pinnacle of our engineering capability, the very best we can do when we throw everything we have at the problem of moving fast. And even here, as you are about to see, the light year remains stubbornly, almost mockingly beyond our reach. The space shuttle orbited the Earth at approximately 28,000 kilometers per hour. This is a staggering speed by human standards. At 28,000 kilometers per hour, you could travel from New York to Los Angeles in about 8.5 minutes. At that speed, 1 light year would take 9,461,000,000,000 divided by 28,000, which equals approximately 337,893,000,000 hours, or about 38,560 years. Nearly 39,000 years. For context, 39,000 years ago, Neanderthals were in their final days, soon to become extinct. Homo sapiens were creating the earliest cave paintings in Europe. The last ice age was in full swing. Massive glaciers covered much of North America and northern Europe. If a space shuttle had launched from Earth 39,000 years ago and flown in a straight line toward the stars at its orbital speed, it would just now be reaching the 1 light year mark. Just now. After all of recorded human history, all of civilization, all the rise and fall of empires, all the wars and revolutions and discoveries and inventions, the shuttle would just be arriving at 1 light year. The International Space Station orbits at a similar speed, about 27,600 kilometers per hour. So its travel time would be almost identical, approximately 39,100 years. The ISS, that marvel of international cooperation that has been continuously inhabited since November 2000, that orbits the Earth roughly every 90 minutes, would need nearly 40,000 years of straight-line travel to cover 1 light year. The astronauts aboard the ISS, zipping around the planet at nearly 28,000 kilometers per hour, are moving at a speed that is 0.0000086% the speed of light, less than 100,000th of a percent. Apollo 10, which holds the record as the fastest crewed vehicle in history, reached a speed of 39,897 kilometers per hour during its return from the moon in May 1969. The crew of Thomas Stafford, John Young, and Eugene Cernan were moving faster than any humans before or since. At that speed, 9,461,000,000,000 divided by 39,897 equals approximately 237,130,000,000 hours, or about 27,060 years. About 27,000 years ago, it was the last glacial maximum, the peak of the last ice age. Humans were painting the walls of the Chauvet Cave in France, creating some of the oldest known artworks in human history. Sea levels were about 120 meters lower than today. The English Channel did not exist because Britain was connected to mainland Europe by dry land. The world was a fundamentally different place. And that is how long it would take the fastest crewed vehicle ever to cover 1 light year. Now we get to the robotic explorers, the spacecraft that have ventured farther from Earth than any human has ever traveled. Voyager 1, launched on September 5, 1977, is currently the most distant human-made object in existence. After receiving gravity assists from Jupiter and Saturn, Voyager 1 is traveling at approximately 61,000 kilometers per hour relative to the Sun. It has been traveling for over 48 years as of today, and it is currently about 24.5 billion kilometers from Earth, or roughly 164 astronomical units. That sounds impressive, and it is, but let us put it in light-year terms. Voyager 1's current distance from Earth is approximately 0.0023 light-years, less than 1/4% of 1 light-year. After nearly half a century of travel at 61,000 kilometers per hour, Voyager 1 has covered less than 0.25% of a single light-year. At its current speed, 9,461,000,000,000 divided by 61,000 equals approximately 155,098,000,000 hours, or about 17,700 years. It would take Voyager 1 approximately 17,700 years to travel 1 light-year. And to reach Proxima Centauri, if it were heading in that direction, which it is not, it would take about 75,000 years. Voyager 1 carries the famous Golden Record, a gold-plated copper phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth. It includes greetings in 55 languages, music ranging from Bach to Chuck Berry, natural sounds like birdsong and whale calls, and 116 images of Earth and its inhabitants. It was intended as a message in a bottle cast into the cosmic ocean, a way of saying we were here to any spacefaring civilization that might encounter it in the distant future. But the chances of Voyager ever being found by anyone are essentially zero. Space is so vast, so empty, so overwhelmingly large, that Voyager 1 could travel for billions of years and never come close to another star system. It will drift through the Milky Way as a silent, cold, dead artifact, long after the sun has burned out and the Earth has been consumed, carrying its golden record as a testament to a civilization that once existed on a tiny blue planet orbiting an ordinary yellow star in an unremarkable corner of the galaxy. There is something profoundly beautiful and melancholic about that. Voyager 2, Voyager 1's twin, launched 16 days earlier on August 20th, 1977, is traveling somewhat slower at about 55,000 kilometers per hour. It took a different trajectory, visiting Uranus and Neptune. the only spacecraft to visit these outer giants, and is heading in a different direction than Voyager 1. At 55,000 kilometers per hour, 1 light-year would take Voyager to approximately 19,600 years, even longer than Voyager 1. New Horizons, the spacecraft that gave us our first close-up look at Pluto in July 2015, is traveling at about 58,000 kilometers per hour relative to the Sun. It was the fastest spacecraft at launch, leaving Earth at approximately 58,536 kilometers per hour, making it the speediest departure from our planet ever achieved at the time. At its cruising speed, 9,461 billion divided by 58,000 equals about 163,120 million hours, or roughly 18,600 years. New Horizons showed us a world of stunning complexity at Pluto, with mountains of water ice, plains of nitrogen ice, and a thin atmosphere of nitrogen and methane. It revealed that even the most distant, seemingly dead worlds in our solar system are dynamic and fascinating places. But in terms of interstellar travel, New Horizons, like the Voyagers, is heartbreakingly slow. 18,600 years to cover 1 light-year. And now we come to the current record holder, the fastest human-made object ever created, the Parker Solar Probe. And this is where things get really interesting. The Parker Solar Probe, launched in August 2018, was designed to study the Sun's outer atmosphere, the corona, by flying closer to the Sun than any spacecraft in history. To achieve its close solar passes, it uses gravity assists from Venus to gradually tighten its orbit. And as it swings close to the Sun, something remarkable happens. Just as a ball on a string moves faster when you shorten the string, the Parker Solar Probe accelerates enormously as it dips close to the Sun's immense gravitational pull. At its closest approach, known as perihelion, the Parker Solar Probe reaches speeds of approximately 692,000 kilometers per hour relative to the Sun. Let me say that again. 692,000 kilometers per hour. That is about 192 kilometers per second. At this speed, you could travel from the Earth to the Moon in about 33 minutes. You could fly from New York to Tokyo in about 17 seconds. This is the fastest any human-made object has ever moved, and it is a genuinely astonishing feat of engineering. So how long would it take the Parker Solar Probe, at its maximum speed, to travel 1 light-year? Here is the calculation. 9,461 billion divided by 692,000 equals approximately 13,672 million hours, or roughly 1,560 years. 1,560 years. Let that sink in. The fastest object humanity has ever created, moving at a speed so extreme that it defies everyday comprehension, would still need over 1,500 years to travel 1 single light-year. 1,560 years ago, it was approximately 466 AD. The Roman Empire in the West had just fallen or was in its final death throes. The Dark Ages were beginning in Europe. The great civilizations of the Maya were flourishing in Central America. Islam had not yet been founded. The Middle Ages were just beginning. The entire modern world, everything we know and take for granted, every nation, every institution, every technology, all of it was still more than a millennium in the future. That is how long it would take our fastest spacecraft to travel 1 light-year, and that is only 1 light-year. The nearest star is 4.24 times farther. The center of our galaxy is 26,000 times farther. The nearest major galaxy is 2.5 million times farther. I want you to really sit with this fact, because it is the central revelation of this entire video. Even our absolute best technology, the fastest thing we have ever built, is so incomprehensibly slow compared to the speed of light that interstellar travel with current technology is effectively impossible within human timescales. The gap between human speed and light speed is not a gap that we can bridge with incremental improvements. It is not like we just need a slightly better engine or a slightly more aerodynamic spacecraft. The gap is fundamental, existential, and enormous. Our fastest spacecraft moves at about 0.064% the speed of light, less than 1/10 of 1%. We need to go more than 1,000 times faster just to bring travel times down to years instead of millennia. That is not an engineering challenge. That is a physics challenge. That is a civilization-defining challenge, and it is a challenge that will likely take centuries, if not longer, to solve. Let me now put this into even sharper focus by looking at the actual distances in space around us and what they mean in terms of travel time. Because 1 light year, as we have seen, is already an almost impossible distance, but in the context of the actual universe, 1 light year is practically nothing. It is a tiny step. A baby's first stumble in a marathon that stretches beyond the horizon. Let us start close to home. The Moon is about 384,400 kilometers from Earth. With the Apollo missions, we reached the Moon in about 3 days. The space shuttle, if aimed at the Moon, could have gotten there in about 14 hours at orbital speed. The Parker Solar Probe at maximum speed could reach the Moon in about 33 minutes. These are manageable timescales. The Moon is close. Mars, at its closest approach, is about 55 million kilometers away. At the Parker Solar Probe's top speed, that is about 80 hours, a little over 3 days. Practical, if challenging. Even at space shuttle speed, Mars is reachable in about 82 days. This is why Mars is the next logical step in human space exploration. It is close enough to be achievable with technology that is within our grasp. Jupiter, the largest planet, is about 628 million kilometers from Earth at closest approach. Parker Solar Probe, speed, about 38 days. Saturn, about 75 days. Neptune, about 6 months at Parker Solar Probe speed, or about 12 years at Voyager 2 speed, which is roughly how long Voyager 2 actually took to reach Neptune. Pluto, at an average distance of about 5.9 billion kilometers, about a year at Parker Solar Probe speed, or about 9.5 years at New Horizons speed, which again is roughly how long New Horizons actually took. These numbers are big, but they are manageable. Decades of travel, perhaps, but not centuries, not millennia, not millions of years. The solar system, as vast as it is within our technological reach. We have already sent robots to every planet and to several moons, asteroids, and comets. We have even sent spacecraft out of the solar system entirely. Our engineering is up to the task of exploring our local cosmic neighborhood. But now, let us step outside the solar system, and everything changes. The edge of our solar system, depending on how you define it, extends roughly 1 to 2 light years from the Sun if we include the Oort cloud, that vast spherical shell of icy objects that marks the outermost boundary of the Sun's gravitational influence. We have never sent a spacecraft to the Oort cloud. At Voyager 1 speed, reaching the inner edge of the Oort cloud, roughly 2,000 to 5,000 astronomical units from the Sun, where 1 astronomical unit is 150 million kilometers, would take somewhere between 300 and 800 years. The outer edge, at perhaps 100,000 astronomical units, or nearly 1.6 light years, would take Voyager 1 about 28,000 years. We cannot even reach the edge of our own solar system in a human lifetime with our fastest technology. And then comes the void. Between the outermost edge of our solar system and the nearest star, there is essentially nothing. No planets, no asteroids, no comets. Just the near-perfect vacuum of interstellar space, with a few atoms of hydrogen per cubic centimeter, some cosmic rays, some interstellar dust, and the faint cold glow of the cosmic microwave background radiation. This void extends for over 4 light-years until you reach Proxima Centauri, our nearest stellar neighbor. Proxima Centauri is a red dwarf star, much smaller, cooler, and dimmer than our Sun. It has about 12% of the Sun's mass and about 14% of the Sun's diameter. If you replaced the Sun with Proxima Centauri, you would barely be able to see it from Earth. It was discovered in 1915 by the Scottish-South African astronomer Robert Innes, who found that it was slightly closer to us than the other 2 stars in the Alpha Centauri system, Alpha Centauri A and Alpha Centauri B. These 3 stars form a triple star system, with Proxima Centauri orbiting the main pair at a great distance. In 2016, astronomers announced a discovery that sent shockwaves through the scientific community. They had found a planet orbiting Proxima Centauri, a potentially habitable planet. It was named Proxima Centauri b, and it orbits within the star's habitable zone, the region where liquid water could exist on a planet's surface. Proxima b has a minimum mass of about 1.17 Earth masses, making it roughly Earth-sized. It orbits its star in just 11.2 days, at a distance of about 7.5 million kilometers, much closer than Mercury is to our Sun. But because Proxima Centauri is so much dimmer and cooler than the Sun, this close orbit places the planet squarely in the habitable zone. There are caveats, of course. Proxima Centauri is a flare star, meaning it periodically erupts with powerful bursts of radiation that could strip away a planet's atmosphere. Proxima b may also be tidally locked, meaning one side permanently faces the star while the other is in eternal darkness. Whether it has an atmosphere, whether it has water, whether it could support life, these are all open questions. But the mere fact that the nearest star has a potentially habitable planet has electrified the field of exoplanet research and given a concrete, tantalizing target for future interstellar exploration. Let us now calculate the travel times to Proxima Centauri at 4.24 light-years away using the speeds we have already discussed. Walking at 5 kilometers per hour, approximately 915 million years. Let me repeat that. Walking to the nearest star would take nearly 1 billion years. That is about 20% of the age of the Earth itself. Driving at 120 kilometers per hour, about 38 million years. Commercial airplane at 900 kilometers per hour, about 5 million years. Space shuttle at 28,000 kilometers per hour, about 163,000 years. Voyager 1 at 61,000 kilometers per hour, about 75,000 years. This is sometimes cited as the standard benchmark for how long it would take our most distant spacecraft to reach the nearest star, if it were heading in the right direction. Parker Solar Probe at 692,000 kilometers per hour, about 6,600 years. Even our fastest spacecraft would need over 6 millennia to reach the nearest star. 6,600 years ago, the earliest civilizations in Mesopotamia were just beginning to develop agriculture and writing. If the Sumerians had launched a Parker Solar Probe at Proxima Centauri, it would just be arriving now. These numbers tell a clear and sobering story. With current technology, interstellar travel is impossible on any timescale relevant to human civilization, let alone human lifetimes. But humans are not a species that accepts impossibility lightly. We have always pushed boundaries, always sought to go farther, faster, higher. And so, there are proposals, some grounded in established physics, others speculative and exotic, for technologies that could potentially close the gap between us and the stars. Let us explore them. Current rocket technology, the kind that powered the Apollo missions and launches the Space Shuttle and the Falcon 9, relies on chemical propulsion. Chemical rockets work by burning fuel, a propellant, and expelling the hot exhaust gases at high speed out of a nozzle, propelling the rocket forward by Newton's third law of motion. For every action, there is an equal and opposite reaction. Chemical rockets are powerful, reliable, and well understood. They can produce enormous thrust, which is essential for lifting heavy payloads off Earth's surface against the pull of gravity. But they have a fundamental limitation. The energy content of chemical propellants is relatively low. The best chemical rocket fuels, like liquid hydrogen and liquid oxygen, can produce exhaust velocities of about 4.4 kilometers per second. This sets a ceiling on the speeds that chemical rockets can achieve. The fundamental challenge is described by the Tsiolkovsky rocket equation, one of the most important equations in spaceflight. It tells us that the speed a rocket can achieve depends on two things: the exhaust velocity of its propellant and the ratio of the rocket's total mass, including fuel, to its empty mass. To go faster, you need more fuel. But more fuel means more mass, which means you need even more fuel to accelerate that mass, which means even more mass, and so on in a vicious cycle. For chemical rockets, the math becomes brutal very quickly. To reach even a small fraction of light speed, you would need a fuel-to-payload ratio that is astronomically, impossibly large. For example, to accelerate a 1-ton payload to just 10% the speed of light using the best chemical propellants, you would need approximately 10 to the power of 1,400 tons of fuel. That is a number so large that it exceeds the mass of the observable universe by an absurd margin. Chemical rockets are simply not the answer for interstellar travel. They are like trying to cross the Pacific Ocean in a rowboat. They work brilliantly for getting around our local pond, the solar system, but they are fundamentally inadequate for the ocean of interstellar space. So, what are the alternatives? Let us go through them one by one, from the most near-term and practical to the most exotic and speculative. Ion propulsion represents a significant step up from chemical rockets in terms of efficiency, though not in terms of raw thrust. Ion engines work by ionizing a propellant, usually xenon gas, and accelerating the ions using electric fields to extremely high speeds. The exhaust velocity of an ion engine can be 10 to 20 times higher than that of a chemical rocket, which means much better fuel efficiency. NASA's Dawn spacecraft used ion propulsion to orbit both the asteroid Vesta and the dwarf planet Ceres, becoming the first spacecraft to orbit two different bodies beyond Earth. The downside is that ion engines produce very little thrust, often measured in millinewtons. A single ion engine produces about as much force as a sheet of paper resting on your palm. But in the vacuum of space, where there is no friction or air resistance, even this tiny thrust, applied continuously over months and years, can build up to significant speeds. The next, NASA Evolutionary Xenon Thruster. Ion engine has been tested and could potentially propel a spacecraft to speeds of about 90,000 kilometers per hour. At that speed, 1 light-year would still take about 12,000 years, and Proxima Centauri would take about 50,000 years. Better than chemical rockets, but still far from practical for interstellar travel. Nuclear thermal propulsion offers another improvement. In a nuclear thermal rocket, a nuclear reactor heats a propellant, typically hydrogen, to extremely high temperatures, and the hot gas is expelled to produce thrust. Because nuclear reactions release millions of times more energy per unit mass than chemical reactions, nuclear thermal rockets can achieve exhaust velocities about 2 to 3 times higher than chemical rockets, and they can produce substantial thrust. NASA actually developed and tested nuclear thermal rocket engines in the 1960s and 70s under the NERVA, Nuclear Engine for Rocket Vehicle Application, program. The technology worked. Engines were built, tested, and performed well. But the program was canceled due to budget cuts and shifting priorities. A nuclear thermal rocket could significantly reduce travel times within the solar system, perhaps getting to Mars in 3 to 4 months instead of 6 to 9 months. But for interstellar travel, the improvement is still incremental. Speeds might double or triple compared to chemical rockets, but we need improvements of thousands of times, not 2 or 3 times. Now we get to something truly audacious: nuclear pulse propulsion, also known as Project Orion. This was a concept studied in the late 1950s and 1960s by a team including the legendary physicist Freeman Dyson and weapons designer Ted Taylor. The basic idea is breathtaking in its boldness: propel a spacecraft by detonating nuclear bombs behind it. Yes, you read that right. The Orion concept involved a massive spacecraft with a large, reinforced pusher plate at the rear. Nuclear bombs would be ejected behind the spacecraft and detonated one after another. The plasma and radiation from each explosion would slam into the pusher plate, giving the spacecraft an enormous push forward. Shock absorbers between the plate and the crew section would smooth out the ride. The beauty of this concept is that nuclear explosions release staggering amounts of energy, and by using them as propulsion, you could achieve speeds that are simply impossible with any other known technology. Theoretical analyses suggested that a large Orion-type spacecraft could reach speeds of 5 to 10% of the speed of light. At 5% the speed of light, 1 light year would take about 20 years. At 10% light speed, about 10 years. And Proxima Centauri could be reached in 42 to 85 years. These are still long journey times, spanning human lifetimes, but they are at least within the realm of conceivable missions. The Orion project was eventually canceled, not because the physics did not work, but because of the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. And honestly, there are legitimate concerns about launching a spacecraft powered by thousands of nuclear explosions from Earth's surface, given the radioactive fallout. But as a deep space propulsion system, ignited far from Earth, the concept remains one of the most promising known approaches to interstellar travel. Some modern researchers have revisited the idea using smaller, more efficient nuclear devices, and the basic physics remains sound. Project Daedalus was a study conducted by the British Interplanetary Society between 1973 and 1978, designed as a more refined approach to interstellar travel than the brute force nuclear explosions of Orion. Daedalus proposed using nuclear fusion, the process that powers the Sun, as a propulsion system. Specifically, it would use inertial confinement fusion, in which tiny pellets of deuterium and helium-3 would be ignited by electron beams, producing controlled fusion explosions at a rate of 250 per second. The exhaust from these fusion reactions would be directed out the back of the spacecraft, propelling it forward. The Daedalus design called for a 2-stage spacecraft that would accelerate for about 4 years, reaching a maximum speed of about 12% the speed of light, and then coast to its target, Barnard's star, about 5.96 light-years away. The total journey time would be approximately 50 years. At 12% light speed, 1 light-year would take about 8.3 years. This is a dramatic improvement over anything we can currently build, but there are significant challenges. The Daedalus design required 50,000 tons of fuel, including large quantities of helium-3, which is extremely rare on Earth but may exist in significant quantities on the Moon and in the atmospheres of gas giant planets. The spacecraft itself would be enormous, about the size of a large naval vessel. And we have not yet achieved sustained nuclear fusion in a laboratory, let alone in a spacecraft engine. Project Icarus, a successor study begun in 2009, has been working to update and improve the daedalus design using modern technology and understanding. The fundamental approach remains the same: fusion-powered interstellar travel. But the details are being refined to account for advances in fusion research, materials science, and spacecraft design. Both Daedalus and Icarus represent serious physics-based approaches to interstellar travel, even if they are decades or centuries away from realization. Solar sails offer a completely different approach to space propulsion, one that requires no fuel at all. A solar sail is a large, thin, reflective membrane that harnesses the pressure of sunlight or laser light to propel a spacecraft. Just as wind fills the sails of a ship, photons from the sun push against a solar sail, gradually accelerating it. The force is tiny, but in the vacuum of space, continuous photon pressure over weeks and months can build up significant speeds. And because a solar sail carries no fuel, it can accelerate for as long as it continues to receive light, giving it a theoretical advantage over fuel-limited rockets. Several solar sail missions have already flown. JAXA, the Japanese space agency, launched Icaros, interplanetary kitecraft accelerated by radiation of the sun, in 2010, becoming the first spacecraft to successfully demonstrate solar sailing in interplanetary space. The Planetary Society launched LightSail 2 in 2019, which successfully used solar sailing to raise its orbit around Earth. These missions proved that the concept works, but the speeds achieved were modest. Solar sails using only sunlight are limited by the intensity of solar radiation, which drops off rapidly with distance from the sun. But what if you replaced sunlight with a powerful laser? This is the idea behind the Breakthrough Starshot initiative, and it is one of the most exciting concepts in modern space exploration. Breakthrough Starshot was announced in 2016 by billionaire Yuri Milner, with the backing of the late Stephen Hawking and other prominent scientists. The concept is radical. Build an array of powerful ground-based lasers, combine their beams, and use the resulting intense light to push a fleet of tiny, lightweight spacecraft called starships to speeds of up to 20% the speed of light. Each starship would be about the size of a postage stamp, weighing only a few grams, attached to a thin, lightweight sail about 4 meters across. The laser array on Earth would focus an enormous amount of energy, about 100 gigawatts, onto the sail for a few minutes, accelerating the tiny spacecraft to 20% of light speed. At this speed, the starship could reach Proxima Centauri in approximately 20 years. Once there, it would fly through the Proxima Centauri system, capturing images and data, and beam the information back to Earth using a tiny onboard laser. The return signal, traveling at the speed of light, would take another 4.24 years to reach us. So from launch to first data, we would be looking at about 24 years. That is within a single generation. For the first time in human history, we have a plausible concept for reaching another star within a human lifetime. Of course, there are enormous technical challenges. Building a 100 gigawatt laser array is far beyond our current capability. Keeping the laser focused on a tiny sail at distances of millions of kilometers requires extraordinary precision. The starship must survive the intense radiation of the laser during acceleration. It must survive for 20-plus years in the harsh environment of interstellar space. At 20% light speed, even a tiny grain of interstellar dust would impact the sail with the energy of a small bomb. Communication from a chip-sized spacecraft across interstellar distances is an enormous challenge, and the starship would be traveling so fast that its flyby of Proxima Centauri would last only seconds, giving it an extremely limited window to collect data. Despite these challenges, the Breakthrough Starshot team is making progress. They have been developing the laser technology, the sail materials, the communication systems, and the miniaturized electronics needed. It remains speculative and decades away from realization, but it is grounded in known physics. No new physics is required. No exotic materials, no undiscovered forces, just extreme engineering. And that is a crucial distinction, because it means the laws of physics, as we understand them, do not forbid it. Antimatter propulsion represents perhaps the ultimate in fuel efficiency, at least within the bounds of known physics. When matter meets antimatter, they annihilate each other completely, converting 100% of their combined mass into energy, according to Einstein's E equals mc squared. Compare this to nuclear fission, which converts about 0.1% of mass to energy, or nuclear fusion, which converts about 0.7%. Chemical reactions convert an even tinier fraction. Antimatter annihilation is the most efficient energy source possible. 1 gram of antimatter, annihilating with 1 gram of matter, would release about 180 trillion joules of energy, equivalent to about 43 kilotons of TNT. That is nearly 3 times the energy of the Hiroshima bomb from a single gram. A spacecraft powered by antimatter annihilation could theoretically reach speeds of 50 to 90% the speed of light, depending on the design. At 50% light speed, 1 light year takes 2 years. At 90% light speed, just over 1 year. These are human timescales. With antimatter propulsion, the stars become reachable within a single human lifetime. But there is a catch, and it is an enormous one. Antimatter is the rarest, most expensive substance in the universe, at least for us. We can produce it in particle accelerators, but only in absurdly tiny quantities. CERN, the world's premier particle physics laboratory, produces only a few nanograms of antihydrogen per year. A nanogram is a billionth of a gram. At current production rates and costs, 1 gram of antimatter would cost approximately $62.5 trillion and would take about 1 billion years to produce. To power a practical interstellar spacecraft, you would need kilograms of antimatter, perhaps even tons. We are not just a little bit short of what we need. We are cosmically, ludicrously short. Antimatter propulsion is physically possible, but practically, it is beyond anything our current civilization can accomplish. It may require a completely different level of technology, energy production, and industrial capability, perhaps achievable by a future civilization centuries or millennia more advanced than ours. Fusion propulsion, as we discussed with Project Daedalus, remains one of the most promising middle ground options. Nuclear fusion is the process that powers every star in the universe, including our Sun. In the Sun's core, hydrogen atoms are fused together to form helium under immense pressure and temperature, releasing enormous amounts of energy. If we could harness this process in a controlled way, we could use it to power spacecraft to speeds of 5 to 15% of the speed of light. The challenge, as you probably know, is that we have not yet achieved sustained net energy positive fusion on Earth, despite decades of research and billions of dollars of investment. The ITER project in France, the world's largest fusion experiment, is working toward demonstrating that fusion can produce more energy than it consumes. But even if successful, ITER is an experimental reactor, not a power plant, and certainly not a spacecraft engine. Still, progress in fusion research is accelerating, and many physicists believe that practical fusion power is achievable within the next few decades. Once we have fusion power on Earth, the path to fusion-powered spacecraft becomes much clearer. There was also considerable excitement and controversy around the M drive, a hypothetical engine proposed by Roger Scheuer that appeared to produce thrust without any exhaust, seemingly violating Newton's third law. If it worked as claimed, it would revolutionize space travel, because a thrustless engine means you do not need fuel, and you can accelerate indefinitely. NASA's Eagle Works laboratory at Johnson Space Center tested an M drive, and initially reported small but measurable thrust. However, subsequent, more rigorous experiments by multiple teams around the world failed to reproduce these results, and the scientific consensus as of early 2025 is that the M drive does not work as claimed. The apparent thrust in early experiments was likely due to experimental error, thermal effects, or other mundane explanations. It remains a cautionary tale about the importance of rigorous testing and peer review in science. Now, let us dive deep into Einstein's relativity, because it is not just an abstract theory. It has profound practical implications for what interstellar travel at high speeds would actually look like, and it offers both challenges and, surprisingly, some hope. Einstein's special theory of relativity, published in 1905, rests on those two postulates I mentioned earlier. The laws of physics are the same in all inertial reference frames, and the speed of light in vacuum is constant for all observers. From these two simple starting points, Einstein derived consequences that were so radical, so counterintuitive, that they seemed like science fiction. And yet every single one of them has been confirmed by experiment. The first and most famous consequence is time dilation. Time itself, the very ticking of clocks, the beating of hearts, the rate of aging, slows down for objects moving at high speeds relative to a stationary observer. This is not a metaphor. It is not a philosophical abstraction. It is a physical, measurable reality. The amount of time dilation depends on the speed of the moving object, and it is described by the Lorentz factor, usually denoted by the Greek letter gamma. The Lorentz factor equals 1 divided by the square root of 1 minus v squared over c squared, where v is the speed of the object and c is the speed of light. At low speeds, the Lorentz factor is essentially 1, meaning there is no noticeable time dilation. But as speed increases toward the speed of light, the Lorentz factor grows rapidly. Let me give you some specific numbers to illustrate. At 10% the speed of light, which is about 30,000 kilometers per second, or 108 million kilometers per hour, the Lorentz factor is about 1.005. This means time for the moving object passes about 0.5% slower than for a stationary observer. Barely noticeable. At 50% the speed of light, about 150,000 kilometers per second, the Lorentz factor is about 1.155. Time passes about 13% slower. Noticeable, but not dramatic. At 90% the speed of light, the Lorentz factor jumps to about 2.294. Time passes more than twice as slowly. If you traveled for 1 year at 90% light speed by your onboard clock, about 2.3 years would pass on Earth. At 99% the speed of light, the Lorentz factor is about 7.089. Time passes 7 times slower. 1 year of your travel time corresponds to about 7 years on Earth. At 99.9% light speed, gamma is about 22.37. 1 year for you is 22 years on Earth. At 99.99% light speed, gamma is about 70.71. 1 year for you is 71 years on Earth, and at 99.9999% light speed, gamma is about 707.1. 1 year of travel for you corresponds to 707 years passing on Earth. The implications for interstellar travel are extraordinary. If you could somehow accelerate a spacecraft to 99.9999% the speed of light, a journey of 1 light year would take 1 year and a tiny fraction from Earth's perspective, but from the traveler's perspective, it would take only about half a day. The travelers would barely have time to eat lunch before arriving at their destination, while everyone they left behind on Earth would have aged a year. This leads to the famous twin paradox, a thought experiment that perfectly illustrates the strangeness of time dilation. Imagine two twins, Alice and Bob. Alice stays on Earth. Bob boards a spacecraft that travels to a star 1 light-year away at 99.99% the speed of light, then turns around and comes back. From Alice's perspective on Earth, Bob's round trip takes a little over 2 years, 1 light-year each way at near light speed. But from Bob's perspective, due to time dilation with a Lorentz factor of about 70, the entire round trip took only about 10 days. When Bob returns, he has aged only 10 days while Alice has aged over 2 years. They are no longer the same age. Bob is now younger than his twin sister, not by a trivial amount, but by nearly 2 years. And if the journey were longer, the difference would be even more dramatic. A round trip to Proxima Centauri at 4.24 light-years, at 99.99% light speed, would take about 8.5 years Earth time, but the traveler would experience only about 44 days. The traveler would return to find that friends and family had aged 8.5 years. At 99.9999% light speed, the same trip would take 8.5 Earth years but only about 4.4 days for the traveler. The asymmetry is mind-boggling. This means that, in principle, time dilation makes interstellar travel within a human lifetime possible for the travelers, even if centuries or millennia pass on Earth. A crew traveling at 99.99% light speed could reach the center of our galaxy, 26,000 light-years away, in about 26,000 years Earth time. But they would experience only about 368 years of subjective time. At 99.9999% light speed, they would experience only about 37 years, well within a human lifetime. They could, in theory, travel to the Andromeda Galaxy, 2.537 million light-years away, in 2.537 million years Earth time, but in only about 3,587 years of subjective time at 99.9999% C. And at even higher fractions of C, with enough nines after the decimal point, you could theoretically cross the entire observable universe within a human lifetime in terms of subjective experience, while billions of years pass for the rest of the universe. But there is a dark side to this. The travelers would be chrononauts in the truest sense. They would be traveling not just through space but through time, effectively leaping into the future. Everyone they knew on Earth would be long dead when they returned. Civilizations could rise and fall. The Earth itself might be unrecognizable. There would be no going back to the world they left. This is not just a physical journey. It is an existential one. It is a one-way trip to the future with all the isolation and loss that implies. The astronauts would gain the stars but lose their world. The second major consequence of special relativity is length contraction. Just as time slows down at high speeds, distances contract in the direction of motion. At 50% light speed, distances shrink by about 13%. At 90% light speed, they shrink by about 56%. At 99.99% light speed, they shrink by over 99%. This means that from the traveler's perspective, 1 light-year of distance becomes much shorter. At 99.99% C, 1 light-year shrinks to about 0.014 light-years, or about 133 billion kilometers, less than 1.5% of its true length. This is, in a sense, the same phenomenon as time dilation viewed from a different angle. The traveler crosses 1 light-year in a short time, not because they are moving faster than light, they are not, but because, from their perspective, the distance they need to cross has shrunk dramatically. Both effects, time dilation and length contraction, are two sides of the same coin, both arising from the fundamental geometry of spacetime, as described by special relativity. The third consequence is the relativistic increase in effective mass. As an object approaches the speed of light, the energy required to accelerate it further increases without bound. It is often described as the object's mass increasing, though modern physicists prefer to say that the object's relativistic momentum increases. Whatever the terminology, the practical result is the same. The closer you get to light speed, the harder it becomes to go faster. At 90% light speed, you need about 2.3 times as much energy per unit of acceleration as at low speeds. At 99% light speed, about 7 times. At 99.99%, about 71 times. And at 100% light speed, an infinite amount of energy. This is the fundamental reason why no massive object, no spacecraft, no astronaut can ever reach the speed of light. You would need infinite energy, and there is not that much energy in the entire universe. The speed of light is not just a speed limit imposed by some cosmic traffic law. It is a fundamental property of the geometry of spacetime. Reaching it would require not just more energy, but an infinite amount of energy, which is by definition impossible. This energy requirement is the key practical barrier to high-speed interstellar travel. Even getting to 10% of light speed requires an enormous amount of energy. To accelerate a 100-ton spacecraft, about the mass of the International Space Station, to 10% of the speed of light would require roughly 4.5 times 10 to the 19th joules, which is about equal to the total energy output of the United States for an entire year. To reach 50% light speed, you would need about 10 times more. To reach 90% light speed, about 100 times more. And to reach 99.99% light speed, thousands of times more than the entire annual energy production of all human civilization. The energy requirements are not just large, they are civilizationally impossible with our current energy infrastructure. To become an interstellar civilization, we would first need to become a fundamentally more energetic civilization, perhaps harnessing the full output of the sun, a Type 2 civilization on the Kardashev scale, or even the full output of our galaxy, Type 3. But here is the beautiful thing about relativity. Despite all these challenges, it does not actually forbid interstellar travel. It makes it incredibly difficult and energy expensive, but not impossible. The laws of physics permit a spacecraft to travel at 99.99% the speed of light. The laws of physics permit time dilation to compress a journey of light years into months or years of subjective time. The laws of physics permit length contraction to shrink vast cosmic distances into manageable ones from the traveler's frame. The barriers are engineering and energy, not physics. And that distinction matters profoundly, because engineering and energy are problems we can, in principle, solve. They may take centuries or millennia to solve, but they are not forever beyond the reach of intelligence and determination. Before we move on, let me share 2 pieces of real-world evidence that prove time dilation is not just a theoretical construct, but a cold, hard fact of nature. First, GPS satellites. The Global Positioning System works by using a constellation of 31 satellites orbiting the Earth at about 20,200 kilometers altitude, moving at about 14,000 kilometers per hour. Their onboard atomic clocks run slightly slower than clocks on Earth due to their speed, special relativity time dilation, but slightly faster due to weaker gravity at their altitude, general relativity time dilation. The net effect is that GPS satellite clocks gain about 38 microseconds per day compared to ground clocks. If we did not correct for this relativistic effect, GPS positions would drift by about 10 kilometers per day, rendering the system useless. Every time you use GPS navigation on your phone, you are relying on corrections derived from Einstein's theories of relativity. Relativity is not abstract philosophy. It is built into the technology you use every day. Second, muon decay. Muons are subatomic particles produced when cosmic rays hit molecules in the upper atmosphere, about 15 kilometers above the Earth's surface. Muons are unstable and decay very quickly, with a half-life of about 2.2 microseconds. Even at nearly the speed of light, in 2.2 microseconds, a muon should travel only about 660 meters before decaying. So, muons produced at 15 kilometers altitude should not be able to reach the Earth's surface, and yet they do. We detect vast numbers of muons at ground level. The explanation is time dilation. The muons are moving so fast, about 99.8% the speed of light, that time in their reference frame is dramatically slowed. Their 2.2 microsecond half-life, from our perspective, is stretched to about 35 microseconds, giving them enough time to travel 15 kilometers and reach the ground. Every muon that reaches the Earth's surface is living proof of Einstein's time dilation. Now, let us venture into the most exotic and speculative territory. Technologies that go beyond simply moving very fast and instead propose to cheat the speed of light barrier entirely. These are the warp drives, the wormholes, the science fiction turned theoretical physics ideas that make space geeks like me dizzy with excitement, even as the sober physicist in me cautions that they may never be realizable. The Alcubierre warp drive is perhaps the most famous of these concepts. In 1994, the Mexican theoretical physicist Miguel Alcubierre published a paper that electrified both the physics community and the science fiction world. Working within the framework of Einstein's general theory of relativity, which describes how mass and energy warp the fabric of space-time, Alcubierre showed that it was mathematically possible to create a warp bubble around a spacecraft. Inside this bubble, space-time would be flat, and the spacecraft would be at rest, but the bubble itself would be moving through space-time. Specifically, space-time in front of the bubble would be contracted, pulled toward the spacecraft, while space-time behind the bubble would be expanded, pushed away. The net effect would be that the bubble and the spacecraft inside it would move through space at effectively faster than light speeds, without the spacecraft itself ever locally exceeding the speed of light. This is an incredibly subtle and important distinction. The speed of light is a local speed limit. Nothing can travel through space faster than light locally, but space-time itself can expand or contract at any rate. This is actually already happening in our universe. The most distant galaxies are receding from us at speeds greater than the speed of light due to the expansion of space. They are not moving through space faster than light. Rather, the space between us is expanding faster than light. Alcubierre's warp drive exploits this same principle. The spacecraft is not moving through space at all. Space is moving around the spacecraft. It is like being on a moving sidewalk at an airport. You stand still on the sidewalk while the sidewalk carries you forward. Technically, you are not walking faster. The ground beneath you is moving. Similarly, a warp drive would not make you travel faster than light. It would make space carry you faster than light. The mathematics of Alcubierre's solution are completely valid within general relativity. The equations work. The geometry is consistent. There is no mathematical flaw. The problem lies in the physical requirements. To create the warp bubble, Alcubierre's solution requires exotic matter, specifically matter with negative energy density. Normal matter, everything we see around us, has positive energy density. Exotic matter with negative energy density would have properties that seem bizarre. It would exert negative pressure, effectively pushing space-time apart rather than pulling it together. Does negative energy density actually exist? The answer is a qualified yes. The Casimir effect, an experimentally verified quantum phenomenon, demonstrates that negative energy densities can exist on very tiny scales. Between two closely spaced conducting plates in a vacuum, quantum fluctuations create a region where the energy density is lower than the surrounding vacuum, effectively negative. The Casimir effect is real, measured, and confirmed. But the amount of negative energy involved is fantastically tiny, and extending it to the scales needed for a warp drive is an entirely different challenge. When Alcubierre first published his paper, calculations suggested that the amount of exotic matter needed would be on the order of the mass energy of the entire observable universe. That was clearly a non-starter. But subsequent work has refined the requirements. In 2012, NASA physicist Harold Sonny White recalculated the energy requirements using a modified geometry for the warp bubble, and found that by adjusting the shape from a flat ring to a more efficient donut shape, the energy requirements could be reduced to something on the order of 700 kilograms of exotic matter, in terms of mass energy equivalent. 700 kilograms is still an enormous amount of exotic matter, given that we can currently produce only the tiniest traces of anything resembling negative energy. But it is a universe apart from the original estimate. It suggests that the concept might, with sufficient advances in physics and technology, eventually move from the realm of pure theory to something approaching engineering. In 2021, physicist Eric Lentz published a paper that took the concept even further. Lentz showed that it might be possible to create a warp bubble using only positive energy without requiring exotic matter at all. His soliton solution involved a specific configuration of space-time curvature that could, in theory, travel faster than light while being consistent with classical energy conditions. This was a remarkable result, though it came with its own caveats. The amount of positive energy required was still stupendously large, and there are questions about whether the solution is physically stable and realizable. Nevertheless, the direction of research is encouraging. Over 3 decades, the warp drive concept has gone from mathematically interesting but physically impossible to extremely challenging but not necessarily forbidden by physics. That is meaningful progress. Wormholes, or Einstein-Rosen bridges, represent another potential shortcut through space-time. A wormhole is a theoretical tunnel connecting 2 distant points in space-time, a kind of cosmic subway that would allow you to travel vast distances without actually crossing the intervening space. The concept arises naturally from general relativity. In 1935, Einstein and Nathan Rosen showed that the equations of general relativity permitted the existence of bridges between different regions of spacetime. Imagine taking a sheet of paper, which represents 2-dimensional spacetime, and folding it so that 2 distant points are right next to each other. A wormhole would be a tunnel punched through the paper connecting those 2 points. Instead of traveling across the paper from one point to the other, you could simply step through the tunnel and arrive instantly. The problem, once again, is physical realizability. For a wormhole to be traversable, meaning you could actually travel through it without being destroyed, it would need to be held open by exotic matter with negative energy density. Without exotic matter, a wormhole would collapse the instant anything tried to pass through it. Kip Thorne, the Nobel Prize-winning physicist who served as scientific consultant for the movie Interstellar, worked out the physics of traversable wormholes in detail in the late 1980s, and concluded that while they were theoretically allowed by general relativity, the exotic matter requirements were forbidding. No one knows how to create or obtain the necessary exotic matter. and it is unclear whether nature permits it to exist in the quantities needed. There is also the question of whether wormholes actually exist in nature. General relativity allows them, but that does not mean they are actually there. Many things are mathematically possible in general relativity that do not exist in the real universe. And even if wormholes did exist naturally, they might be too small, perhaps at the Planck scale, about 10 to the minus 35 meters, too unstable or too distant to be of any practical use. The idea of creating artificial wormholes belongs firmly to the realm of speculative physics, and is, if anything, even more challenging than the Alcubierre warp drive. Quantum teleportation is sometimes invoked in discussions of faster-than-light travel, but it is important to understand what it actually is and is not. Quantum teleportation is a real phenomenon, experimentally demonstrated many times, in which the quantum state of one particle is transferred to another particle instantaneously, regardless of the distance between them. This is possible because of quantum entanglement, a mysterious property of quantum mechanics in which two particles can become correlated, such that measuring one instantly determines the state of the other, no matter how far apart they are. Einstein famously called this spooky action at a distance. However, and this is crucial, quantum teleportation does not transmit information faster than light. It does not teleport matter. It does not allow you to send a message instantaneously. The reason is that to complete the quantum teleportation process, you need to send classical information, which travels at or below the speed of light, from one party to the other. Without this classical information, the receiving party cannot reconstruct the teleported state. This is formalized in the no-cloning theorem and the no-communication theorem of quantum mechanics. Quantum teleportation is a real and fascinating phenomenon, but it is not a faster-than-light communication or travel technology. It does not help us cross 1 light-year any faster. Let me now paint a picture of what it would actually look like to travel at close to the speed of light, because the visual and physical experience would be nothing like what science fiction movies typically portray. At rest, or at low speeds, the universe looks pretty much as we expect. Stars are dots of light in a dark sky. The cosmic microwave background is invisible to our eyes. Space is black. But as you accelerate toward the speed of light, strange things begin to happen. First, there is the Doppler effect. Light from stars ahead of you would be blue-shifted, meaning its wavelength would be compressed, making the stars appear bluer and more energetic. Light from stars behind you would be red-shifted, stretched to longer wavelengths, making those stars appear redder and dimmer. At high speeds, the blue shift becomes extreme. Visible light from ahead becomes ultraviolet, then X-rays, then gamma rays. You would not see stars ahead of you so much as you would be bombarded by high-energy radiation. Meanwhile, stars behind you would be redshifted through infrared into radio waves and effectively vanish. Second, there is the headlight effect, also known as relativistic aberration. Stars would appear to crowd toward the direction of travel, as if you were flying into a tunnel of light. Stars that were to your sides or even slightly behind you would appear to shift forward. At very high speeds, almost all the stars in the sky would crowd into a brilliant, intense circle directly ahead of you, while the rest of the sky behind would be pitch black. Third, there is the relativistic beaming effect. Light from stars ahead would be greatly intensified, making the forward view blindingly bright, while light from behind would be enormously dimmed. The combined effect of blue shifting, aberration, and beaming would make the forward direction a searing blast of high-energy radiation, while the rear would be darker than the deepest void. And then there is the radiation danger. At high fractions of light speed, even the thin gas of the interstellar medium becomes a lethal barrage. Hydrogen atoms that are normally lazily drifting through space at a few kilometers per second would, from the spacecraft's perspective, be slamming into the hull at 99% the speed of light, which means each hydrogen atom impacts with the energy of a cosmic ray. The cumulative effect of trillions of such impacts per second would be like flying into a particle beam. Without massive shielding, the crew and the spacecraft would be destroyed by radiation long before they reached their destination. This is one of the underappreciated challenges of high-speed interstellar travel. The faster you go, the more dangerous the interstellar medium becomes. Now, I want to take a different kind of journey. Instead of exploring how we might traverse a light year, let us explore what exists within that light year. Because the space between stars, the interstellar medium, is not the featureless void that most people imagine. It is a fascinating, dynamic, and in many ways surprising environment. First, let us be clear about what we mean by empty. Interstellar space is the closest thing to a perfect vacuum that exists in nature, but it is not truly empty. The average density of the interstellar medium in our part of the galaxy is about 1 atom per cubic centimeter. That is unimaginably sparse by Earth standards. The air you are breathing right now contains about 25 quintillion, 25 times 10 to the 18th, molecules per cubic centimeter. So, interstellar space is about 25 quintillion times less dense than air. If you took all the interstellar matter in a cubic light-year of space and compressed it, you would get about 0.5 solar masses of material, roughly the mass of a small star. Spread over a cubic light-year, it is incredibly thin, but it is not zero. The interstellar medium is composed primarily of hydrogen, about 70% by mass, and helium, about 28%. With trace amounts of heavier elements like carbon, nitrogen, oxygen, and silicon. Some of this matter exists as individual atoms or ions, the warm and hot phases of the interstellar medium, while some is locked up in molecules, primarily molecular hydrogen, H2, found in dense molecular clouds. And some exists as tiny solid particles, interstellar dust grains, typically made of silicate minerals or carbon compounds, ranging from about 0.01 to 1 micrometer in size. Interstellar dust is particularly important. Although it makes up less than 1% of the interstellar medium by mass, it has an outsized impact on astronomy because it absorbs and scatters visible light. This is why some parts of the Milky Way appear dark when viewed from Earth. We are looking through dense clouds of interstellar dust that block the light from stars beyond. Dust is also the raw material from which planets, asteroids, and ultimately life are made. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was once interstellar dust, forged in the hearts of ancient stars and scattered into space by supernova explosions. For a spacecraft traveling at high speed through the interstellar medium, this tenuous gas and dust becomes a significant concern. At low speeds, the particles are harmless, but at 10% the speed of light, a collision with even a microgram of interstellar dust would release the energy equivalent of a small explosion. At 50% light speed, the energy scales up dramatically due to relativistic effects. At 90% light speed, a single grain of dust impacting the spacecraft would be catastrophic. This is one of the engineering challenges that any interstellar mission must address. How to protect the spacecraft from the accumulated impacts of interstellar medium during a journey of years or decades at high speed. Solutions that have been proposed include magnetic shielding, using powerful magnetic fields to deflect charged particles, physical shields, sacrificial layers of material at the front of the spacecraft, and laser brooms, using forward-pointing lasers to vaporize or deflect incoming particles. None of these have been developed or tested for interstellar conditions, but the physics of each is well understood. The interstellar medium also contains magnetic fields, typically about 1 to 10 microgauss in strength, roughly a millionth of Earth's magnetic field. These fields play a crucial role in the dynamics of the galaxy, influencing star formation, confining cosmic rays, and shaping the structure of nebulae. For a spacecraft, these magnetic fields could be both a challenge and an opportunity. A challenge because they would interact with any charged or magnetized components of the spacecraft, and an opportunity because, in principle, a spacecraft with a large magnetic field generator could use the interstellar magnetic field for braking or navigation. Cosmic rays are another feature of the interstellar environment. These are high-energy particles, mostly protons and helium nuclei, that have been accelerated to near-light speeds by supernova explosions, black holes, and other extreme astrophysical events. Some cosmic rays have truly astounding energies. The highest energy cosmic ray ever detected, the Oh My God particle, observed in 1991, had an energy of about 320 exa-electron volts, 3.2 times 10 to the 20th electron volts, which is the kinetic energy of a baseball thrown at about 100 kilometers per hour, concentrated in a single subatomic particle. Cosmic rays pose a significant radiation hazard to both astronauts and spacecraft electronics on interstellar journeys. On Earth, we are protected by our planet's magnetic field and thick atmosphere, which deflect and absorb most cosmic rays before they reach the surface. In interstellar space, there is no such protection. Long-duration interstellar missions would require substantial radiation shielding, adding to the mass and complexity of the spacecraft. And then there is the cold. The average temperature of the interstellar medium varies widely, from about 10 Kelvin, minus 263 degrees Celsius, in the densest molecular clouds to millions of Kelvin in the hot, ionized gas near supernova remnants. But the general background temperature of the universe, set by the cosmic microwave background radiation, is about 2.725 Kelvin, just barely above absolute zero. In the void between stars, far from any heat source, a spacecraft would radiate away its heat into the cold vacuum and gradually approach this temperature. Maintaining internal warmth for crew and equipment would require continuous energy input. Over journeys lasting decades or centuries, this energy requirement becomes a significant design consideration. There is something deeply contemplative about the nature of interstellar space. It is a realm of almost unimaginable emptiness, cold, and silence. No sound. Sound cannot travel in a vacuum. No warmth, except what you bring with you. No landmarks. The nearest star is still light years away. Just the faint ancient glow of the cosmic microwave background, the echo of the Big Bang, surrounding you in every direction. In a very real sense, a crew traveling through interstellar space would be more alone than any human beings have ever been. They would be beyond the reach of rescue, beyond the reach of rapid communication, beyond the reach of everything they have ever known. The loneliness of interstellar space is not just physical, it is existential. It is a confrontation with the raw vastness and indifference of the universe. Now, let us zoom out and think about what the distance of 1 light year means when we look at the night sky. Because every star you see is telling you a story, not just about what it is, but about when it was. When you look at the night sky, you are not looking at the universe as it is right now. You are looking at the universe as it was at different times in the past, each star showing you a different moment in history, a different when, painted across the canvas of where. The sun's light is 8.3 minutes old when it reaches you, so you always see the sun as it was 8 minutes ago. If the sun were to suddenly change color right now, you would not know for over 8 minutes. The light from Alpha Centauri is 4.37 years old. You see that star system as it was 4.5 years ago. Sirius, the brightest star in the night sky, is 8.6 light years away. You see Sirius as it was when you were about 8 to 9 years younger than you are now. If you are 25, the light from Sirius that is hitting your eyes right now left that star when you were about 16 years old. Vega, one of the brightest stars in the northern hemisphere, is about 25 light years away. The light you see from Vega tonight left that star about 25 years ago. In 2026, you are seeing Vega as it was in 2001, around the time of the September 11th attacks and the launch of the first iPod. Now, let us go further. Polaris, the North Star, is approximately 433 light-years away. The light you see from Polaris tonight left that star around 1593, during the reign of Queen Elizabeth I, when Shakespeare was writing his early plays and Galileo had not yet built his first telescope. Betelgeuse, as I mentioned, is about 700 light-years away. Its light left around 1326. Deneb, the brightest star in the constellation Cygnus, is about 2,615 light-years away. You see Deneb as it was around 589 BC, during the time of the Buddha and Confucius, when the First Persian Empire was rising. The Orion Nebula, that beautiful glowing cloud of gas and dust visible in Orion's sword, is about 1,344 light-years away. The light you see from it tonight left during the 7th century, around the time of the rise of Islam and the early Tang dynasty in China. The pillars of creation, those famous columns of interstellar gas in the Eagle Nebula photographed by the Hubble Space Telescope, are about 6,500 light-years away. The light in that image left the pillars around 4,500 BC, thousands of years before the first Egyptian pyramid was built, around the time when the earliest civilizations in Mesopotamia were just beginning to develop writing. And here is a mind-blowing addendum. There is evidence suggesting that the pillars of creation may have been destroyed by a supernova shockwave about 6,000 years ago. If this is true, the pillars no longer exist. They were obliterated thousands of years ago. But because the light from their destruction has not reached us yet, it is still about 1,000 years away, we continue to see them as if they are still standing. We are gazing at ghosts. Beautiful, luminous, long-dead ghosts. The center of our Milky Way galaxy, home to the supermassive black hole Sagittarius A star, is about 26,000 light-years away. We see the galactic center as it was 26,000 years ago, during the depths of the last ice age, when early humans were creating cave paintings in Europe and hunting mammoths across the frozen steppes. If an alien civilization at the center of the Milky Way were looking at Earth right now with a powerful enough telescope, they would see our planet as it was 26,000 years ago. They would see no cities, no agriculture, no writing, no civilization. Just a world of ice and scattered bands of hunter-gatherers. The Andromeda Galaxy, the nearest major galaxy to our own, is about 2.537 million light-years away. The light we see from Andromeda tonight left that galaxy 2.537 million years ago, during the early Pleistocene, when the first members of the genus Homo were emerging in Africa. Australopithecus was still walking the earth. Our distant ancestors were barely distinguishable from apes. If beings in Andromeda were looking at Earth right now, they would see a planet inhabited by proto-humans, millions of years before any hint of technology or civilization. The most distant objects we can see, galaxies at the edge of the observable universe, are over 13 billion light-years away. Their light has been traveling since shortly after the Big Bang. We see them as they were in the infancy of the universe, when galaxies were first forming, when the cosmos was a violent, chaotic place of intense radiation and primordial gas clouds. These objects may no longer exist, or they may have evolved into completely different forms. We will never know their current state because the light carrying that information will not reach us for billions of years, and by then, our sun will have burned out. The Earth will be gone, and human civilization will be a distant memory, if it is remembered at all. This concept, this idea that looking out into space is looking back in time, is one of the most profound consequences of the finite speed of light. The universe does not have a now in the way we intuitively understand it. There is no single moment that is the present everywhere in the universe simultaneously. Every observation we make is of the past. The only now that exists is our own local moment, and everything we see beyond our immediate surroundings is a report from an earlier time. The farther away we look, the further back in time we see. The universe is a vast time machine, and we are all time travelers, looking into the past every time we lift our eyes to the stars. This leads to one of my favorite thought experiments. Imagine an alien civilization on a planet orbiting a star that is exactly 65 million light-years from Earth. If they had a telescope powerful enough to resolve individual features on Earth's surface, what would they see? They would see the Earth as it was 65 million years ago, the time of the dinosaurs. They would see Tyrannosaurus rex stalking through ancient forests. They would see pterosaurs soaring through warm, humid skies. They would see the asteroid that would end the Mesozoic era hurtling through space toward its fateful impact in what is now the Yucatan Peninsula. They would have no idea that 65 million years after the scene they are witnessing, the descendants of tiny, shrew-like mammals that survived the asteroid impact would build civilizations, develop technology, and begin asking questions about the cosmos. To them, Earth is a dinosaur planet, and there is nothing we can do about it. We cannot send them a signal saying, "Hey, things have changed a lot since then," because even if we could send that signal at light speed, it would take 65 million years to reach them, and they would receive it 65 million years in their future. An alien 2,000 light-years away would see Earth during the time of the Roman Empire. They would see cities of marble and brick, roads stretching across continents, legions marching across Europe. They would see a world that had developed writing, philosophy, mathematics, and complex political systems, but no electricity, no powered flight, no radio signals. An alien 250 light-years away would see Earth during the American Revolution, the Age of Enlightenment, the beginnings of the Industrial Revolution. They might notice cities growing, ships crossing oceans, the first hints of large-scale human impact on the landscape. An alien 100 light-years away would see Earth at the beginning of the 20th century, just before the First World War, just before the first radio broadcasts began emanating from our planet. And an alien 50 light-years away, with a sensitive enough radio telescope, might pick up the earliest television broadcasts leaking out into space, including the 1936 Berlin Olympics, one of the first major televised events. Our electromagnetic footprint, the bubble of radio and television signals that has been expanding into space since the early 20th century, extends about 100 light-years in all directions. Within this bubble, encompassing roughly 15,000 star systems, an alien civilization with the right technology could, in principle, detect our signals. Beyond this bubble, we are invisible. We have not announced our presence. Compared to the Milky Way, which is 100,000 light-years across and contains 100 to 400 billion stars, our 100 light-year bubble of signals is vanishingly small. It covers about 0.1% of the galaxy's diameter, we have barely whispered into the cosmic darkness. And this brings us to one of the great questions of our time, the Fermi paradox. The Fermi paradox, named after the Italian-American physicist Enrico Fermi, is the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for or contact with such civilizations. Fermi reportedly posed the question over lunch at Los Alamos National Laboratory in 1950. Where is everybody? The reasoning behind the paradox goes something like this. There are billions of stars in our galaxy. Many of those stars have planets. Some of those planets are in the habitable zone where liquid water could exist. Life has arisen at least once, on Earth, so presumably it could arise elsewhere. Given the age of the galaxy, about 13.6 billion years, and the time it took for intelligent life to evolve on Earth, about 4 billion years, there has been ample time for multiple intelligent civilizations to arise. Even a civilization only slightly more advanced than ours should be capable of interstellar colonization over millions of years, which is a tiny fraction of the galaxy's age. So the galaxy should be teeming with advanced civilizations. Yet we see no evidence of them, no alien signals, no alien artifacts, no alien visitors, nothing. Silence. Why? Many solutions have been proposed, and the vast distances we have been discussing today play a central role in several of them. Perhaps the simplest explanation is the sheer scale of space. Even if intelligent civilizations are relatively common, the distances between them may be so vast that contact is effectively impossible. If the average distance between civilizations is thousands or tens of thousands of light years, then the speed of light itself acts as a barrier to communication and travel. A message sent from one civilization to another might take thousands of years to arrive. The sending civilization might not even exist anymore by the time a reply could come back. In a galaxy where nothing can travel faster than light, civilizations might be like isolated islands in an ocean too vast to cross. They might look up at the sky and wonder if anyone else is out there, just as we do, and never find out. Then there is the great filter theory, which suggests that somewhere on the path from simple chemistry to spacefaring civilization, there is a step that is extraordinarily difficult or unlikely, a filter that most potential civilizations never get past. If the filter is behind us, meaning it is something we have already passed, like the origin of life, or the evolution of complex cells, or the development of intelligence, then we may be one of very few civilizations to make it this far, and the galaxy is mostly barren of intelligent life. If the filter is ahead of us, meaning it is something we have not yet faced, like nuclear war, climate catastrophe, or some other existential risk, then the cosmos may be littered with the ruins of civilizations that rose and fell before they ever reached the stars. The Fermi paradox does not have a definitive answer, and the role of light-year distances in shaping it is profound. It is entirely possible that we are not alone, but that the universe is simply too large and light is too slow for us ever to find out.